In this slide, we'll do some examples of DTFS. In the first example, we want to find a DTFS of a sinusoid given by some cosine. We'll use two methods. One is the Euler's equation and the other one is the direct computation of xn using DFT. We are given this equation xn. Xn is expressed with the amplitude of A and omega at 8 pi divided by 40. If you simplify, basically this is pi over 5. So it is a cosine at pi over 5 radian per sample with a phase shift of pi over 3 and an amplitude of A. Let's use the Euler's equation first. Euler's equation breaks down the cosine into two complex exponential. And in fact, as we have said, DTFS also breaks down any signals into complex exponential. So in fact, by Euler's formula, we are immediately analyzing the equation in terms of sum of complex exponential, and therefore we can identify the magnitude and the phase at the frequency we want. The frequency we want is pi over 5. Remember, a cosine is the sum of complex exponential at the positive pi over 5 as well as the negative pi over 5. The phase remains the same inside, but at the negative frequency, the negative will distribute such that at the negative frequency, the phase is negated. So therefore, the phase max spectrum will be odd symmetry, while the magnitude spectrum is even symmetry, because A over 2 is the same at a positive frequency as well as the negative frequency. Now, to be very explicit, what we then do is that we open up this bracket over here and distribute this EJ pi over 3 to be outside, to be seated with the same side as the magnitude. So we have the magnitude and the phase at this frequency, pi over 5. And then again, we have A over 2 here, and this negative and the phase will become a negative phase. So you have a magnitude and a negative j pi over 3 as a phase at the negative frequency minus pi over 5. So this is how we do. Later on you will see that the magnitude and the phase spectrum is exactly these values, A over 2, pi over 3 at positive and the negative frequencies. Now, let's see how we do it if we are going to do it by brute force. By brute force here, we are talking about using a computer to generate xn and then taking the Fourier transform or the DFT of it. So let's study this equation. First, we have to figure out what is the period. So you realize that if this is pi over 5 for the omega, we need to find a capital N such that this is true. And we figure out how to do this in our tutorials. I will not go through this. Basically, we have now found that capital N equals to 10. Well, so what do we do now? So if you are sitting in front of MATLAB, you basically let n equals to 0 to 9 and you generate this sequence. So xn now is a vector with 10 numbers generated by this equation here. To find the DFT, we use FFT. FFT is the fast version of DFT, and then we simply take FFT of xn. This guy will produce xk, the DFT coefficient of xn. To get ck, the DTFS coefficient, remember we have to divide by n. So this is 1 over n, FFT of xn will give you the DTFS. How do we get the magnitude and the phase? Ck is a complex number. To get the magnitude, we use this, the magnitude of the number. To get phase, we use the angle of the number. Okay, so it's angle Ck if you're writing in MATLAB. Now, you must be thinking why is this needed? Due to numerical precision, some of the the magnitude CKs are very small. So the phase there is actually due to numerical precision error. We should ignore them when we plot. So we are only plotting for CKs, the phase for magnitude greater than 0.001. So let's see our result. So here, when we have k equals to 0 is here, and because our signal is repeating at every 10 samples in the frequency spectrum, it is also repeating at every 10 sample. So C0 and C10 are theoretically the same guy. C1 and C11 are the same signal. And C minus 1 is the same signal as C9 because capital N is equals to 10. Okay, so here we are plotting across 2 cycles, so you can explicitly see. This plot is the phase plot. This plot is a magnitude plot. We're only plotting until 9. So C9 is actually C minus 1 over here. The magnitude, when we plotted, is A over 2. This is exactly what we expected. And at C1 is positive pi over 3 for the phase. C minus 1 is negative pi over 3, which is odd symmetry. Why C1? Why is C1 why is it k equals to 1? Remember, we are dividing 2 pi over 10. So this is pi over 5 times k. So the signal is pi over 5. Therefore, we only need to choose k equals to 1 to achieve the pi over 5 angular frequency for this cosine. And hence, k equals to 1 is the interesting point. And what about k equals to minus 1? There. At minus pi over 5 is the k equals to minus 1. This is the magnitude and this is the phase. So again, this is how we have done how to find the DTFS representation using Euler's equation as well as direct computation using MATLAB. You can watch this video with more examples by Adam Panagos. Thank you.